KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
Hi students, from today onwards we are going to start Neet classes, right? And it is the first chapter in our Neet classes, which is dual nature of radiation and matter. Okay, so first chapter in our Neet classes dual nature of light, right? So in this chapter dual nature of light, we start with work function or threshold energy. Work function or threshold energy, right? So regarding the Neet point of view, here this chapter has 2 questions weightage, but it is not fixed based on the previous questions I am telling, right? So definitely 2 questions. And in this chapter the most important topic is photoelectric current. Photoelectric current, okay, that is what the phenomena is, photoelectric effect. Okay, right. And before entering into this synopsis, I need to tell you what is meant by photoelectric current. Photoelectric current, right? As we are going step by step, we will discuss very clear what is photoelectric effect and how to observe the photoelectric effect, that and all. But right now I will tell you just the phenomena. What is photoelectric effect? What is photoelectric effect, right? Okay. Students, you know that in a metal, some metals are conductors of electricity. Some metals, that is what generally metals are good conductors of electricity, right? Not only metal, generally metal is also a material. Metal is also a material, right? So not only metal, you can take a piece of wood, you can take a piece of rubber, right? So whatever you are taking, so material means some of the materials which allows electrical energy and some doesn't allow. So here regarding the allowing of electrical energy, so if it allows means it is said to be a conductor, and if it doesn't allow means it is said to be an insulator, right? Okay. But what I am saying here is, regarding the periodic table of chemistry, the electronic configuration, and what are the free electrons, and you already know that what is meant by valency. What is meant by valency, right? So now what I am saying is the number of free electrons, right? The number of free electrons are more means, you can expect more high conductivity. You can expect high conductivity. That is what transferring of energy from one place to another place in an circuit, in an electrical circuit, is as much as speed, right? That's why here the number of electrons present in the outermost orbit is simply said to be valency, right? So it differs from metal to metal. That valency differs from metal to metal, right? But why I am saying all these things means here in our phenomena, in our natural phenomena, right? In our natural phenomena, you can get it. You can see in this natural phenomena. If you take a metal surface. If you take a metal, what is the surface of metal, right? Just when you are going to allow a light, that is what invisible form of energy, onto a metal surface, metal surface or a metallic surface, you know, the electrons will come out. The electrons comes out from the metal, right? So when a free metallic surface or when a metallic surface is exposed to the electromagnetic radiation, then emission of electrons takes place. This is what we are calling it as photoelectric effect. That is important discussion in our chapter. That is what dual nature of light, right? So this photoelectric effect is the natural phenomena. Just we are in a discussion. That's it. It is a natural phenomena, right? So when a metallic surface is exposed to the electromagnetic radiation means what? Is a light, is a picture of light, is an invisible form of energy, right? So which consists of oscillating electric field and magnetic field, and both are perpendicular to each other and also perpendicular to the direction of propagation of light, right? So this is what we discussed in the chapter of electromagnetic waves from our board syllabus, right? Okay. So when a metallic surface is exposed to the invisible form of energy, that is light or electromagnetic radiation, the emission of electrons will take place. This is what natural phenomena. And how many number of electrons will come? What is the speed of the electron, right? And these and all the things depends upon many factors. You know, we have various metals, for example, like platinum, gold, right? And nickel, aluminum, silver, right? So like that we have different metals, right? So that's why this is the phenomena what I am saying. And how many number of electrons are coming out, what is the speed of the electrons, these are all based on different factors, okay, right? Now first I am going to explain what is work function or threshold energy. First I am going to explain you what is work function or threshold energy, right? So throughout this chapter, whenever I am explaining something, you have to keep in mind what is photoelectric effect. Okay, right? Now you see this, what is work function or threshold energy, right? The minimum energy of incident radiation required to eject the electrons from metallic surface is defined as work function of that surface. I will repeat once again. The minimum energy of incident radiation required to eject the electrons from metallic surface is defined as work function of that surface, right? I am going back to the photoelectric effect, right? So in photoelectric effect, what happens? There is a metallic surface. On that metallic surface, a light, that is what the incident radiation, that is what electromagnetic radiation, that is what invisible form of energy, right? So when the light will incident, that is what when the radiation is going to incident, it has certain amount of energy. No, I am only saying that is what it is, an invisible form of energy, right? It has certain amount of energy. So what about that energy? If that energy is too less, that is what very small amount. If that energy is high, a large amount, so what happens? The point is that is what we have different metals. Right? So, but there is a requirement of certain amount of energy, right? If the energy is less than that certain amount of energy, you cannot experience any photoelectric effect, and no electron will come out from the metallic surface. Right? I hope you got it, what I am saying, right? When you take a metallic surface, right? So light is going to incident. That light or incident radiation must have certain amount of energy, right? certain amount of energy. If the energy is less than that certain amount of energy, you cannot experience any photoelectric effect and no emission of electrons from metallic surface. So that certain amount of energy we are calling it as wave function. That certain amount of energy we are calling it as work function. Work function, right? Work function of that surface. Work function of that particular surface or of that metallic surface, right? So the minimum energy of incident radiation required to eject the electrons from metallic surface is defined as work function of that metallic surface, okay, right? And see this mathematical relations, it is what, this is what W naught is the notation or a symbol we are using to represent work function. That is equal to, what is work function basically? It is energy. See here, the minimum energy, right? So that formula E is equal to h nu. Even in the chemistry also in atom chapter, right? So we got it, E is equal to h nu, that is equal to hc by lambda, right? The same thing we are writing here, that is what W naught is equal to h nu naught, that is equal to hc by lambda naught, hc by lambda naught. And what are the units of energy, whether it is scalar or vector, right? And what is the dimensional formula? This and all we came to know. That is what here, joules, right? hc by lambda naught, joules, right? So what is nu naught? Nu naught is a threshold frequency. Nu naught is a threshold frequency, right? Nu naught is a threshold frequency, right? See here, next. I'll tell you what is threshold frequency, we will come to know, right? Till that you have to remember just nu naught is a threshold frequency, and at the same time, lambda naught is the threshold wavelength, right? So nu naught is the threshold frequency and lambda naught is the threshold wavelength, okay? That is what work function W naught is equal to h nu naught, that is equal to hc by lambda naught joules, right? And we had another unit for energy, that is what smallest unit, okay, it is electron volt. It is electron volt. 1 electron volt is equal to 1.6 into 10 to the power of minus 19 joules. 1 electron volt is equal to 1.6 into 10 to the power of minus 19 joules, okay, right? So the same relation what we are writing, this is the relation in joules, right? So shall we write this relation in electron volt? Yeah, definitely. See here, work function in electron volt, W naught. See in the bracket they mentioned, it is what, electron volt, that is equal to hc by E lambda naught, that is equal to, h is the Planck's constant and c is the speed of light, okay? So every time instead of substituting h value and c value and multiplying, simply they have given one number, that is what, 12375, right? So that is what, 12,375, 12,375 divided by lambda, right? It is what, in terms of angstrom unit, it is what, in terms of angstrom unit, okay? So it is the expression for work function in electron volt, right? Work function of several elements. Work function depends upon the nature of the element basically. So work function of several elements, you can see here, that is what, platinum, right? And gold, nickel, carbon, silicon, copper, right? So this side again aluminium, silver, right? Silver, and then sodium, lithium, potassium, cesium, right? So they have given different elements, right? So for these elements, what is the minimum energy required? What is the minimum for these elements? What is the minimum energy of incident radiation required to eject the electrons from respective metallic surfaces, right? So termed as work function of those metallic surfaces, right? So that is what 6.4 for potassium, right? Sorry, 6.4 for platinum, and 5.1 for gold, and 5.1 for nickel, right? And carbon 5.8, silicon 4.8, and copper 4.7, aluminum 4.3, and silver 4.3, right? And sodium 2.7, lithium 2.5, right? Potassium 2.2, and cesium 1.9. Okay. And if you observe this table here, gold and nickel having the same value, and aluminum and silver also having the same value, right? So like that we have same values for a different pair of metal, okay, element, whatever it may be, right? Next, see this, it is what now we are going to discuss, photoelectric effect. I already told you, but once again we will get here, right? See this, the phenomenon of emission of electrons, from a metallic surface, when illuminated by light of appropriate wavelength or frequency, is known as the photoelectric effect. Right? So I will repeat once again. It is what the important definition. I already told you, but once again I am repeating because of having some information here. That is what the phenomenon of emission of electrons. From a metallic surface, when illuminated by light of appropriate wavelength or frequency, is known as the photoelectric effect, right? So as simple as such, the emission of electrons from a metallic surface, when it is exposed to the electromagnetic radiation of appropriate wavelength or frequency, is known as photoelectric effect. Okay, right. See this. Next, the photoelectric effect was first observed by is a basic person, right? So basic scientist, right? Is a great scientist. The photoelectric effect was first observed by Heinrich Hertz, and it was investigated in detail. It was investigated in detail by Hallworks and Philip Leonard. William Hallworks and Philip Leonard. Okay, right. So these three members are the scientists, so the great scientists. So because of their hard work, we realized the natural phenomena. That is what photoelectric effect, and we are in a discussion according to that. Okay, right. See here. Next, the photoelectric effect is based on the principle of conservation of energy. It is important point. So this directly may come as a theory bit, right? So the photoelectric effect consists. So given 4 options, and you have to choose, that is what conservation of energy, right? So here nothing. So photoelectric effect is based on the principle of conservation of energy, right? Already what is conservation of energy, right? So energy neither created nor destroyed. Okay. So it can be transformed, it can be converted from one form to another form. Energy neither be created nor destroyed. It can be converted from one form to another form. Total energy in the universe remains constant. This is what the law of conservation of energy, right? So photoelectric effect is based on the principle of conservation of energy, right? Now you can see some experimental setup to observe the photoelectric effect, right? That is what here you can see. This is cathode ray tube. This is called as cathode ray tube, and it is what P and Q, right? So P is cathode and Q is anode, right? So the metallic plates, it is what cathode plate, and it is what anode plate, right? and this P is going to expose to the light of radiation. This P is exposed to the light of electromagnetic radiation. P is exposed to the electromagnetic radiation, and then from this P, that is what cathode, emission of electrons takes place. Emission of electrons takes place, and you see the remaining things also which are present in the experimental setup. We connected this is what a voltmeter here, a voltmeter to measure the potential difference, between cathode and anode. And we connected a milliammeter, that is what ammeter, basically to know the photoelectric current, to know photoelectric current or photocurrent. And there is a battery, right? There is a battery. This is what plus and minus, plus and minus, plus and minus, right? So it is what battery or any other source of potential difference, And this is what rheostat, right? It is what rheostat to change the resistance, present in the circuit, right? So this is the total experimental setup to observe photoelectric effect, right? And this is what cathode on this electromagnetic radiation, that is what the light is going to incident, and from this emission of electrons takes place, right? And this is what cathode ray tube, and vacuum is present inside the cathode tube, right? And you can observe the electrons, that is like a small discharge, right? Small sparks in the form of small, that is what a little sparks, and that is what discharging of, this is what electrons coming, right? Electrons are coming, and electrons are discharged from this metallic surface, right? That is what from cathode to, and basically anode is positive, no? So this electrons will try to travel from cathode to anode, right? That is what this is called as discharging tube, right? Next, see here, and these are the important points. Here we have 6 points, so you please be concentrate. I will explain one by one clearly. See this, right? Two conducting electrodes. One is anode, another one is cathode, are enclosed in an evacuated glass tube, right? So I will repeat once again. First point, two conducting electrodes. One is anode Q, another one is cathode P, are enclosed in an evacuated glass tube as shown in the figure, right? So here we have shown, this is what cathode and this is what anode, right? Next, see the second point. Here, which is, observe carefully, the battery or other source of potential difference. The battery, here this is what battery or any other source, right? Battery or other source of potential difference between an electric field, this is what in between these two, an electric field in the direction from anode to cathode, right? So he is giving the direction of electric field also, that is what from anode to cathode, okay, right? So here you can see, so what is the battery and what is the anode and what is the cathode, you can see in this picture, right? Next, third point, light of certain wavelength or frequency, falling on the surface of cathode, causes a current in the external circuit, causes current in the external circuit called photoelectric current, sometimes photocurrent also. I will repeat once again. Light of certain wavelength or frequency falling on the surface of cathode causes a current in the external circuit called photoelectric current or photocurrent. Okay, right. Next, fourth one, see here. That is what as potential difference increases. Fourth point, as potential difference increases, photoelectric current also increases till saturation is reached. I will repeat once again. As potential difference increases, photoelectric current also increases till saturation is released, right? Saturation is reached. One thing, for example, you have taken some material, that is what, as a cathode. There are only 10 number of electrons. Just imagine, there are only 10 number of electrons, and you are changing the potential difference here. What is the maximum possibility for the electrons? First 2 electrons will come, 3 electrons will come, and based on the potential difference of cathode and anode, and all the 10 electrons comes from, that is what, cathode to anode. After that, what will happen? Even though you are changing the potential difference according to the situation to expect more number of electrons, there is no chance, because only 10 free electrons are present there. So 10 came from cathode to anode. There is no chance for more than that. So this is what we are calling it as saturation period, right? So that only he is saying in fourth point, as potential difference increases, photoelectric current also increases till saturation is reached. Right, next, fifth point, see here. When polarity of battery is reversed, electrons starts moving back towards the cathode, right? When polarity of battery is reversed, right? So polarity of battery is reversed means what? Right? So plate Q is at negative potential, right? And with respect to the plate P, right? So battery is reversed means plate Q is at negative potential with respect to plate P. So whatever we have, see here, now it is what, positive to the P and negative to the Q. So reversed means what? So suppose that is what, positive to Q and negative to P, that is what, reversing of a battery. Okay, right. So when polarity of battery is reversed, electrons starts moving back towards the cathode, okay, right. Next, see the last point, that is what, sixth point here. At a particular negative potential of Q, and the current will become 0. At a particular negative potential of plate Q, right? At a particular negative potential of plate Q, see what happens here. We are increasing the negativity of Q. So when you are increasing the negativity of Q, what happens? The electrons basically having negative charge now. So when you are increasing the negativity of potential Q, the electrons will not reach Q and they will send back to the cathode. But it is not possible at low, that is what, it is not possible at whatever the point we want, but it is possible at certain frequency, right? At certain potential. So that's what we are calling it as here. Observe carefully. At a particular negative potential for plate Q, no electron reach the plate Q and the current will become 0. So this negative potential is called as stopping potential, and which is denoted by V0. Okay. And one more important point here, that is what, so we are saying kinetic energy of photoelectrons in terms of stopping potential. So maximum kinetic energy of photoelectrons in terms of stopping potential will therefore be, so kinetic energy, that is what, maximum kinetic energy is equal to maximum kinetic energy is equal to, it is what, stopping potential, and you observe that modulus is there. So we are taking only the magnitude, that is what, modulus of V0, and the unit is electron volt. Okay, right. So this is about first class from dual nature of light. Okay, we will continue in the next class. Thank you.